Hello, everyone, and welcome. Thank you for joining us for this session on the key strategies to streamlining design workflows and conduct performance analyses on facade designs. As you get settled, a few reminders before we get started. Not use the chat box to ask any questions for today's presenter. Instead, use the Q&A. With the Q&A feature, attendees can like a question and that will move it to the top of the list. As always, the webinar content and additional resources will be available on the AIA California website shortly after the session. Today's session, focused on achieving better daylighting and EUI targets, is brought to you by Cove Tool. The session qualifies for one AIA HSW learning unit for those who watch live. AIA California staff will report those units for you once you have finished the session. And to introduce our presenter, Nilesh Bansal is the Director of Sustainability at Cove Tool. His primary focus is on product development, supporting research efforts and guiding the AEC industry in defining their organizational strategy for adopting sustainability as a key parameter to help them move towards data-driven empirical design decision-making. Thank you so much for being here today. Please take it away.
Perfect. Thanks, Rebecca. I'm going to go ahead and share my screen, and I might have some bandwidth issues, so I'm going to turn off the video for a quick second. Perfect. Right. So we're going to go ahead and get started. The topic for today's session is optimizing facades to achieve better daylit and high performance spaces with lower embodied carbon. And first things first, the learning objectives for the session today is at the end of the session, we'll be able to comprehend what are the key daylighting metrics. And we'll be talking about three things in specific, which is SDA, which stands for spatial daylight autonomy. The second metric is ASE, or annual sunlight exposure, and the third is window to wall ratios. And these three metrics play a critical role in the building's overall daylighting and performance in general. The second thing we'll see is we'll try to identify some design decisions that impact the daylighting and the availability of daylighting in a space. We'll also learn to compare different facade design strategies for each different facade. And then we look at a couple of real life case studies and understand how design teams were able to effectively improve the daylighting and improve the performance of the space, and also optimize for cost and carbon and energy. In terms of the agenda, the first thing we'll cover is just making the business case for adopting sustainability. Then we'll go through the key terms, like I mentioned before. We'll discuss in detail what these things mean and how people have been using them in the industry in the design process. Then we'll discuss quickly what is the facade guidance feature, and we'll use a web-based app that we have been developing in-house. And I think you people might have used the app sometime before as well. Just show you exactly how we have gamified the whole experience and helping people select the right design strategies. I'm gonna mute for a second because there's some slight noise here. Perfect. So, and then once we have seen what the facade guidance feature does for us, we'll discuss a couple of design strategies and use just look at the case studies that people have used design strategies to improve daylighting and performance in their buildings. And then we'll have a quick Q&A session towards the end. And Yudiksha is also online. If you have any questions as we go through the session, she'll be trying to answer the questions live for you, but we'll also keep some questions towards the end, and we'll definitely try and answer those. Perfect. So the very first thing we want to go through is making the business case for adopting sustainability. So we all know, like, the US cities are adopting stricter and more stringent energy codes. We have seen the codes getting more stringent in the last 30 years. I guess we have become more aggressive in the last 3 years. We are seeing all the states are now adopting more and more recent versions of ASHRAE. So the codes are getting more and more stringent. Also, in terms of what we have seen in the past, let's say if we are looking at this graphic from 1975 to 2010 or 2015, we have almost seen that buildings which were required to have an EUI of, let's say, 100 are consistently asked to have an EUI of about 30, which is a 70% drop. And even from 2004 to 7, we saw a 5% EUI reduction. From 2004 to 2010, we saw a 30% EUI reduction. And from 2004 to 2013, it's a 50% EUI reduction. So we are seeing a significant drop in the requirements for meeting these targets. So that definitely demands for higher performing buildings. The one thing that we are seeing, which is good for us, is that the supply chains are also catching up. So buildings which were high performance used to be consistently more expensive as compared to traditional buildings. But because of these issues being resolved, the industry catching up, we are seeing higher performing buildings not being that expensive as well. So we are definitely making some progress there. Also, we conducted a survey about 1,000 architecture firms and engineering firms, and it was revealed that more than 48% of the RFPs they're receiving or RFPs that have been floated out have sustainability requirements. So that definitely indicates that we have a high requirement for having sustainable designs, better daylighting, high performance design and architecture. We also know that the green buildings have a higher market value. That means if you're looking at from the perspective of developers or tenant or owners, the developers are looking at these buildings because they sell faster, they are lower in design and construction costs, they have higher sale prices. The tenants think they are higher market value to green buildings is because they want to lease the buildings which improve their health and well-being, they increase their productivity, and the owners are looking at these buildings because they have lower maintenance costs, operational costs, they reduce the downtimes, and then there's a couple of combined things that people are looking at. For example, the lower refurbishment costs, it improves their corporate image, prestige value, and other stuff. So green buildings definitely have a higher market value as compared to their traditional counterparts. And then from a design perspective, let's say the graphic that we're looking at is basically showing you the project's life cycle from pre-design to schematic design to design development, all the way to construction administration and operation. And what this is trying to say is basically any change that we make, let's say in the earlier design stages or the schematic design till the design development, the cost of that design change is fairly low. So you can just make a change, go through multiple different iterations and just see what the changes are and how does it impact the overall process. But then if you start making changes, let's say towards the construction documentation stages, procurement or construction administration or CA stages, every change you make will have a significant impact because you will make a change. It's going to affect a number of different design documents. You have to go edit them. That takes additional time. That's going to delay the project. So the cost of design changes is fairly high as you move along in the process. So it's important to just validate all the design decisions early on as much as you can and iterate very fast so as to save you all those extra VE efforts towards the end. So we look at a couple of key terms in terms of daylighting analysis. The very first term we want to talk about is what is daylight modeling. So daylighting is the practice of using 3D simulations, using 3D simulation software to predict the pattern of controlled natural light to illuminate a space inside a building. The daylight quantity and quality are critical factors to any buildings. And what this web-based interface, the Cove tool, is doing is basically it's using the weather files Tregenza Sky, which has 576 subdivisions to project various climatic conditions onto your model and the building's interior. And these analysis planes record the intensity and duration of conditions to generate your results. So the three graphics we are looking at the bottom, the first one is the total radiation. The second one is basically showing you the total radiation from a different perspective. The third graphic we are seeing is just a daylighting simulation of the SDA for that specific space. And we'll be showing you in detail a couple of these case studies and explaining what these really do. So the very first time we want to talk about is the spatial daylight autonomy, or SDA. Basically what SDA does, or the scientific definition of SDA is, it describes the percentage of floor space that receives at least 300 lux of daylighting for more than 50% of the annual occupied hours on the horizontal work plane, which is 30 inches above the floor, which is very scientific definition. But what it basically means is you're trying to understand this metric tells you how much daylighting are you getting in the space. The higher the number is, the better daylighting you're getting in the floor space. So if you're looking at this graphic in the center here, basically what this signifies is for this specific floor plate, in the central areas or these aisles where you have a lot of skylights, you're getting a lot of good daylighting. We also have to look at the factor from a glare perspective, which I'm going to explain in a second. But this just means like in the central areas, we're getting a lot of good daylighting in that floor space. There's a couple of darker patches here. which is probably in the range of 10 to 30%, which are not getting enough daylighting. So that's a clear design advice for us. Maybe we need to increase the window to wall ratios, or maybe the configuration of how we're looking at different window options. The next one is ASE, or annual sunlight exposure, or annual solar exposure in this case. What this basically says is how much percentage of floor space is getting above 1,000 lux of daylighting for more than 250 occupied hours. And so that's a scientific definition. But in a simpler term, this metric directly tells us what the glare situation is inside the floor plate. So if you're getting a number, let's say about 10% or less, you will be able to achieve the lead points that LEED B 4.0 is asking for. If you're anywhere from 10 to 20%, you can provide a narrative of how you will control the glare in that space and still achieve the lead points. If you're above 20%, it means you will not get a lead point. You have to bring that 20%. You'll have to bring that number from 20% or over to less than 20% or less than 10%. So these graphics are kind of telling you what the story is in that floor plate. For example, if you're looking at this graphic, you're seeing a couple of darker patches here. That basically says they're getting a lot of glare. So as to pass, you have to be below 250 occupied hours. So if all the green areas are basically not getting a lot of glare, so they're ideal. I've seen this happen a lot of time in the industry where people are trying to provide glare mitigation strategies on all the different facades, even though they're not getting enough glare. This is a very important metric for all projects, because now you can understand if you want to reduce the glare on the project, you don't really have to provide glare mitigation strategies on all the different facades. You can pretty much select the facades which are getting a lot of glare, just provide the strategy and save on that additional spending for maybe providing automated blinds on the other sides of the facades, which are not really getting a lot of glare. Definitely saves a lot of resources and time and energy and money from the owner's perspective too. Why is really daylighting important? So there's a lot of different scientific studies that have been conducted, which basically says daylighting is definitely important for it keeps the occupants, makes the people more alert. It's directly proportional to improved mood of the occupants. And definitely, if you have a better daylit space, you'll see some additional energy savings, because you wouldn't need a lot of artificial lighting in that space too. The next important metric that we have to talk about is the window to wall ratio, or WWR. Basically, what this says is it refers to the percentage of a given above grade wall that is fenestration. That means it's giving you the ratio of the fenestration that's above grade as compared to the total gross wall above grade area. So in this case, if you're looking at this graphic, this is just telling you, if you're looking at the whole wall, if this is the fenestration, that's about 10% window to wall ratio. If you go to the right, you would see 20%, 30%. And if you achieve, let's say 80% to 100%, you would basically see all the facade is basically a fenestration. So it's a 1-to-1 ratio. It's 100% window to wall ratio. The next thing, what are we really using for calculating the daylighting metrics? We're using a ray tracing method, which basically says we'll trace the ray back from an object to the light source, and we'll put a plane in the middle. Just like in this case, you would see there's a plane in the middle, and we'll project the wherever there's interference with the object and the light, we will project that on the plane, and that basically tells you how much daylighting are we getting. And that's like a very simplified ray tracing method we're using to calculate all the daylighting analysis and metrics. In terms of what facade guidance feature means, within the web-based app, we have a feature that's the facade guidance tool. What this is doing is basically, and I'm sure you have seen this thing in the industry a lot. We always have a question about, let's say if you're talking about a southern facade, what kind of shading strategy works for a southern facade? If you're talking about eastern facade, should we go for vertical shading? Should we go for horizontal shading? What shading strategies are most effective, and what shading strategies are not effective? Or do we even need shading in that specific facade? And I've seen this happen almost all the time, where people actually model a strategy first, and then they go back and try and conduct an analysis and trying to understand or validate if that strategy works well. And if it doesn't work well, they will come up with a different configuration in order to justify what strategies are working or not. What we have done here is basically provided an experimental space. So designers can just come in and say, we will go through multiple different options, and then we'll see exactly what strategy works for what kind of an orientation. So you might just go to the southern facade and say, we will try verticals versus horizontals. Similarly, we'll go for riven windows versus slit windows, and we'll see exactly what configuration leads to what kind of a performance. And then once we have decided, that we have found an effective strategy, then we can actually go back to our original model those strategies, because we already educated in terms of what works and what doesn't work. So it saves you a lot of time modeling those objects, trying to not validate after you've done the design, but being really proactive in terms of design. And I'm going to show you exactly how this works on the website, on the web-based app as well. So this is some more information about using the facade guidance feature. At this point, let me just quickly jump to the actual app so I can show you what that looks like. Perfect. So this is the facade guidance feature we have within the app. You can see how they are different. This is the interface. Towards the left, you have a lot of different features that you can use to conduct all types of building performance analysis. But we're going to just talk about the facade analysis feature, which is this guy right here. And you can see how there are different orientations listed right here. So basically what's happening is once you have the geometry uploaded to the app, you would see only the orientations which exist in your actual model. So in this case, they're just north, south, east, and west orientations for the model. So we just select a certain specific orientation. Let's say we are selecting the southern facade. The very first thing you would see is the window to wall ratio. Basically, we are trying to replicate the exact window to wall ratio that we have with the original model. So if you're going to the southern facade, you'd see 55% window to wall ratios. If we go to the western facade, you'll have a different window to wall ratio, which is an exact replica of how the window to wall ratio, what the number is for that western facade. And then I'm going to let it load for a second. 1 second here. Perfect. So once you have done that, you can just come back here. This is an experimental setup. So what we can do is, let's say this is the window that we're working with. We will reduce the window's height by a couple of centimeters here. We'll reduce the window width, distance from the edge. You can change how the window should be configured. You can change the sill levels. Once you've defined a configuration, you can see that every time you make a change here, it's going to show you the impact of that change on the daylighting metrics, which is SDA. And you can just click on this button again. It's going to show you the impact of that change on the AAC as well. So what's happening here is that this setup is very much gamified. That means you might just say, I'm going to select this window, provide a couple of different overhangs. So you will provide 2 different overhangs, and you can see the impact of those overhangs on the ASC and SDA metrics. But then you might just say, what if we go for, instead of going for horizontal shading, we go for a vertical shading device here. So we can just remove the horizontal shades and say, let's provide a couple of vertical fins here and increase their depth. So every time you make a change, you can see the impact of that design decision on the actual SDA and ASC. And once you've kind of defined a clear strategy of each of these facades, now you can take it back to your original model and really optimize that facade and make it perform better. So that's about it from the tool side of things. I'm going to jump back to the PowerPoint presentation. Perfect. So like I already said, how can the facade guidance feature help designers or anybody who's working with this? Basically, it's a very simplified way of modeling stuff. We're not concerned about the dimensions of the actual model. We are just trying to test different strategies and then actually take it back to your original model. This could be done very quickly. It's rapid prototyping. So you don't really have to have a 3D modeling platform to model these things out. You can just jump on the platform, start testing out different strategies and see what works and what doesn't work. And then once you go through multiple different iterations through the facade guidance feature, you will also start understanding exactly how the sunlight is behaving inside your space, what kind of strategies work for different orientations. So it's also a very good educational tool. In terms of the design strategies that designers can look at when they are maybe exploring the facade guidance tool, the very first thing you can do is basically change the different window to wall ratios, just see how does it impact the overall daylighting. You can provide different types of vertical fins. Maybe you can provide one fin versus multiple different fins. Similarly, you can go for horizontal overhangs. For example, we have seen consistently that southern facades, the horizontal fins work better for southern facades as compared to verticals. Similarly, you can have a combination or a fusion of both vertical and horizontal fins, which is basically an egg-crate system. And then you can always have vertical fins and also provide an angle to those fins and have it at slight angle. So it's not really horizontal, it's at an angle. Similarly, you can provide the same strategies for horizontal overhangs. So there's multiple ways you can twist and turn the design to find the right optimized solution, which provides you the least amount of glare, still maximize the daylighting inside, and provides the visual comfort that occupants are looking for. And then again, you can keep going through all of these different strategies and see exactly what window configurations work best. In terms of facade strategy, shading devices, we have a number of real examples here that people have implemented. For example, providing east-west shading, vertical fins, side daylighting, which avoids glare very effectively, shading devices outside, providing side daylighting controls as well. And then the north factor. Basically, if you provide windows on the northern facade, you don't really have to even compare the glare. You don't even have to conduct the glare analysis or worry about glare from the northern facade. It's kind of a free daylighting, so it just provides you diffuse daylighting throughout the day without having any issues of the glare and nothing of that sort. In terms of looking at different case studies where people have actually implemented these strategies and made an impact. So we have 3 case studies for you today. The very first case study we have is from the Georgia Tech Campus Center Facade Studies. So in this, what people did, or what the designers did, is basically they compared different options within the facade guidance feature. So the very first thing they did was basically tried a couple of different glazing options. For example, here you can see the default glazing options they had were these guys. They're just 2 windows, basically reflecting the same window to wall ratios they have in the original model. And then the second option they're seeing is basically they switch these 2 type of windows with ribbon windows. And you can see when they make the switch in the windows, the impact on the overall SDA. First, you have just isolated patches of daylighting. Once you go to the ribbon window style, it just makes it more diffuse. And then they went for vertical slits instead of the ribbon windows. And you can see the impact of that. This diffuse daylighting penetrating inside the space now is not that effective though. And then they went for the option 3 where they're providing large openings because this orientation demanded for that. And similarly, in the east facade, they're trying to do a couple of other facade studies, just understanding how these metrics impact, how the different metrics are impacted by, let's say, a single large opening in one area of the facade versus distributed openings throughout the facades, and then having a larger opening on one corner and having some vertical slits on the other side of the facade and seeing if that improves the daylighting. Once they decided on what strategy works best for them, they actually took it back to the original buildings model. And then they also conducted an optimization. And I'm going to explain what that looks like in a second in a different case study. And based on that, they were able to effectively implement all these strategies and lead to a high performance student union center. The second case study we want to look at is the Emory University Campus Life Center. Basically, just providing you some more information about the project. This is basically a case study for Emory University Life Campus. This was a 117,000 square feet area campus. The construction cost came out at $90 million. The architects were Duda Payne Architects, and then you can see the name of the MEP engineers and the contractors. The major highlights of this project is basically they were able to save about $1 million in construction cost by using the cost optimization feature. And I'm going to explain how that cost optimization feature works as well. This led to about a 40% energy savings, and the building was able to achieve LEED Platinum. And throughout the process, they were also able to save a lot of time from design revisions because they had a very integrative automated workflow in which people can jump on the same platform, see the information real time, and coordinate better. In terms of what the process looks like, the very important thing to consider is that when you're trying to optimize a project or working on a high performance project, there's a set number of things you have to follow in a sequence. For example, first you have to determine if you want to go for a new construction versus renovation. Then you have to understand what does the climate look like in that specific area for that project typology so as to be able to implement the right strategies for that area. The third is you want to optimize the project from a passive strategy standpoint. That means you want to look at different shading options. You want to look at orientations, different window to wall ratios, basically facade optimization strategies. Once we have covered all of those aspects is when we jump to the active side of things. That means now you'll start selecting different HVAC systems. You will talk about sizing those HVAC systems or having more efficient HVAC systems, implementing a couple of different strategies such as heat recovery or energy recovery and stuff like that. And once we have kind of done all of these processes and we have optimized the EUI as much as we can, that's when we actually jump to the solar PVs or renewable energy side of things and say, how much of this EUI can be offset by using solar PVs or maybe some other renewable energy sources. So what we are seeing on the screen is basically the the project team, the design team was able to conduct this climate analysis fairly quickly, just understanding different metrics from a climate perspective. What is the relative temperature and humidity in that area? The wind analysis for each month of the year, the adaptive comfort. You can see what the radiation benefit looks like. Again, if you're working on a facade, it's important to know if you can really capture that lower southern sun. What's the benefit of that? Versus if you're on the eastern facade or western facade, what is the intensity of the sun? So you can really design according to that. And then you would see the total radiation graphic here. Psychometric chart is again a great way to understand what strategies would provide the most comfort to the occupants. In this case, you can see that for this specific location, the 24.57%, you can get a lot of comfort just by internal heat gain in this specific area. So this basically tells you if you maybe the evaporative cooling would work for you in that location, maybe it wouldn't. And just following these strategies would lead to a better performing space. Once you've kind of covered that, what the team did was, again, go through multiple different configurations of facade options. In this case, now they're comparing basically two types of window to wall ratios, which is 40% continuous window with 40% large openings, again, isolated to a certain extent, then going for a 60% continuous window, and then looking at 60% large openings. And you can see how these configurations are impacting the overall SDA and the ASD in real time. And then they also were able to benchmark, for example, when you're starting a project, you're trying to understand what benchmarks are we looking at. In this case, as per LEED V4.0 or 4.1, V4.0 actually, you're looking at 55% SDA daylighting, and the glare should be less than 10%. So they understood exactly, so as to achieve the LEED points, what numbers they have to achieve. So they are going through all these configurations to make sure they are providing the best daylighting they can, at the same time minimizing the glare. And similarly, on the western facade, they did another study in which they're trying to understand two larger window configurations as compared to a couple of vertical slits here, as compared to combination facades. And once they had done all these strategies, the next step that they did was basically take these strategies back to the original model and then do an actual daylighting analysis for all the three different levels that they had, which revealed some critical information. In this case, they could see that, all right, the SDA overall for all three levels average was 59%, which is above the 55% they were trying to hit. They also see a lot of glare. So basically they were way off from the number that they were trying to achieve. That means they had to provide a lot of glare mitigation strategies, but they knew exactly where they would have to provide those strategies to reduce the glare. For example, in this case, the level 3 is basically saying there are two critical areas, which is this guy and this guy, which would need some sort of a glare mitigation strategy. Similarly, if you're looking at level 2, there is, again, those two corners, which would need the similar strategies. If you're looking at level 1, in this case, it's more upfront towards this side that you have to provide the glare mitigation strategies. So they were able to actually provide that strategy in the project and make it more effective. Similarly, once you have done the daylighting analysis, now the next thing that we can do is basically propagate all that information about how much daylighting are you getting in the space to your energy models. What that means is, let's say if you choose to provide sensors in the space, we know exactly how much daylighting we need to offset from the EUI, because that will lead to additional energy savings overall. So what the energy analysis, what the design team did for the energy analysis side of things is basically they were able to benchmark their EUI fairly readily in an automated fashion. They knew exactly what the 2030 target is that they're trying to achieve. In this case, the whole building's EUI was at 46%, 46 kBTUs per square feet per year, which is better than the national average. So they could actually quantify this into what percentage of operational carbon does this account for. And then you can also see what number of LEED points would this give them. And then moving across the project, they were actually able to reduce this EUI from 46 by 40%, which is kind of the target that the project team was looking for. And then the last thing that they did was the cost versus energy optimization. So what's happening in the cost versus energy optimization is basically when you are conducting energy simulations, you can go through multiple different options manually. You can provide, let's say you provide a U value of 0.3, you will see an impact. You can provide a U value of 0.25, do a sensitivity analysis, see what the impact of that U value on the overall EUI of the project is. But what if you have to look at all the different pieces in conjunction with each other? That means you want to see what's the impact of the U value on your HVAC systems, on the shading, on the PV, basically everything combined. And that's where the cost versus energy optimization comes in play. what this is basically doing and what the project team was able to do is basically run thousands of different simulations in the backend, trying to provide the best part to the lowest to a high performance building with the lowest cost premium and the lowest EUI. In this case, they ran these thousands of simulations and they can see exactly what combinations of options they should be going for so as to provide the lowest EUI, which they actually achieved. So in this case, the whole building baseline EUI was at 46, just like we saw in the previous pages. We can see the cost for all of these options, which is about 5 million. And then once they optimized the project, they could see that the EUI came down from 46 to 40 in this specific instance, which led to a 22% energy savings. And then also the cost premium is about $2 million, which basically means if you add an extra $2 million to the overall baseline, and using these combination of options, you can actually bring the EUI down from 46 to 40. Similarly, there's multiple different options they were able to achieve. There's a lowest cost bundle here in which they're saying you can actually save $1 million, still bring the EUI down, which will lead to a 1% energy savings as compared to the baseline we saw. And the payback in terms of years is 8 years. Trying to simplify the graphic again, because there were a number of different options that we saw there. What this graphic is basically showing you is, so as to bring the EUI down to 46, you have to just follow this path, which says, if you're looking at the roof R value, if you select this option, if you're looking for the glazing U value, you select this option. If you keep tracing this path, this will lead to an option that has a cost premium with the range that we're looking at. It will provide payback in terms of 0 years. Energy savings would be around 10%. And the EUI is at 46. So that's the first case study that we talked about. The second case study is the Terranova Ranch new office pavilion. This was actually a project in California. So in this case, the owners did not have any specific requirements for sustainability. They were not seeking a high performance building, but what the design team was able to do is basically quickly iterate through many different options. And in doing so, they also defined strategies to reduce the overall EUI and the impact through that building. So basically what happens is the very first thing they did was just to create a sample baseline, understanding what their targets are, what's the 2030 target, what's the 2030 baseline, trying to put your project in the middle of those two numbers so they can know exactly how far you are from the target and how far they have to go. In this case, they will also see the 10% and 55% in terms of the glare and daylighting that they have to achieve. So basically the first thing they have to do is basically benchmarking the project. So what they did was basically create the baseline, which revealed that the value they have is at 43, which is also a 12% operational carbon reduction. In doing so, they also revealed some more information, such as this building is actually heating dominated because of the use case, whatever's going on. The plug loads are also really high. Then they went for an option A, and basically going for the option A, they made two specific changes. They increased the insulation in the walls and the roof. So they went for an R30 walls and R41 roof. When they made that change, that actually reduced the EUI from 43 to 38. So that was like a 5 kBTUs per square feet per year kind of reduction, which is about 20% operational carbon savings. So you can see the savings as compared to the 2030 baselines. And now you can see how it impacted the heating by quite a much, but not towards the equipment side of things. They went for an option B now, in which what they did was make one more change. They changed the glazing, the exterior glazing, and the impact of that change was just 1 kBTUs per square feet per year, which improved the operational carbon savings from 20% to 22% again. And you can see all these metrics readily change. Then they went for a third option in which they added solar PVs on the parking shade structure. And they added a lot of solar PVs because they've already optimized for the systems. They've already optimized for the passive side of things. So once they did that, they could see a massive reduction and also a lot of operational carbon reduction in EUI and carbon both. So now their EUI is at 7.48. And then at the end, the last change that they made was basically an option D, in which they added energy recovery. And once they did that, you can see how it's actually a net positive project now because the EUI is a negative. It's 1.52. So that's how they were able to optimize the project and just reduce the EUI and go below 0. And this way, they were able to always also convince the clients about the benefits of doing so. So that's about it from the presentation side of things. I do want to make sure we have time for questions and answers, and we can always jump back to the platform if you have any specific questions on the web-based interface side of things too. Okay, Yadiksha, do you see any questions from the participants?
Yeah, there were a couple of them. I did
Mhm.
answer them. There are about 4, so
Mhm.
I answered them. But if you want to take a look and add your own insights, that should
Mhm.
work. But it's pretty much covered. Yeah.
Perfect. So I'll just quickly take a look. The first question is there any change for buildings occupied 24 hours per day? So that's a good question. In terms of the daylighting metrics, there is no, the SDA is clearly spatial daylight autonomy, or SDA defines it for the occupied hours from 8 a.m. to 6 p.m. For daylighting side of things. But then from an energy perspective, the occupancy will be defining what the EUI looks like. That means if the building is operational from 8 a.m. to 6 p.m., you would see the impact on the EUI based on that occupancy. But if the building, let's say it's a lab building or it's some other use case, which is operational 24 hours, the EUI would be representing that. But the reason daylighting is not considering 24 hours is because there's no daylighting after 8 p.m. Or 8 a.m. From after 6 p.m. There's not much daylighting. So even if you do have sensors on the building, they will still be not doing or adding any more value because there's no daylighting. So there's no more EUI to be offsetted from that. The second question I'm seeing is, how about sun angle and altitude? Perfect. So that's a great question. When you're looking at, let's say, the facade prototyping tool or facade guidance tool, it's based on your building's or project's location, on your building's climate, because we're using the sky dome for that specific location. So if you're located in California versus, let's say, Boston or some other city or location, it will be representing the areas based on that climate. So it's completely accounted for. So the third question that I'm seeing is, what program was used to create the light glare analysis? So that's again a great question. The program that was used to conduct all these analyses was Cove Tool. That is where we work, Yudiksha and I. It's a holistic and automated building performance analysis software. Basically, what it does is we have plugins developed through all the major, or basically all 3D modeling platforms. That means we will never ask the designers to shift from the existing workflows. If you're using Revit, you can pretty much use Revit to upload your geometry to the web-based app, and pretty much everything else is automated. That means all the aspects of location, climate, geometry, the local applicable energy code, everything is automated for the users. So using the tool, you can pretty much conduct daylighting analysis in like 30 minutes or even less, including the geometry upload time. And if you're seasoned users, you can pretty much do it in 10 minutes. I hope that answered that question. And the next question I'm seeing is, can we elaborate on the adaptive comfort climate analysis slide? Absolutely. Let me just go back to the tool here. So now I'm jumping away from the PowerPoint and actually to the actual app. And I can also cover a number of different questions if you have about the app in specific. And since we are talking about climate, I'll go through all of these diagrams. The first thing you would see is the relative temperature and humidity. I think it's a fairly simple graphic to understand. Next is radiation by sky segment. It's just telling you what's the intensity of the sun as it moves throughout. You can see there are patches here in this specific location where the sun is kind of strong. There's a lot of radiation. You would see some blue patches where there's not much sun. But the question was about the adaptive comfort. So you would see all, 1 second. Yeah, so in this case, what's happening is you would see this graphic is basically showing you the evening, daytime, morning time, and nighttime. And it's also showing you the adaptive comfort. So if you're in the red zone, basically it's not comfortable. You want to be somewhere in the middle here. And that's basically showing you the information for the whole year, the same graphic, but for the whole year. So you would see the months from January to December. You would see the time of the day. This is from 12 to 12. And you can see how all of these are turning from white to blue to reddish in the summertime. And you want to be somewhere in the middle, because if you're too low, it's too cold. If you're too hot, like too high, it's too hot. So you're trying to be somewhere in the middle. Similarly, if I keep moving forward, you would see the radiation benefits again. low intensity, low angle sun is really good for southern facades. Let's say if you're talking about the summertime, the sun is fairly high. You're trying to cut down on the sun, so you can provide some shading devices, some horizontal shading on the southern facades. The sun is fairly low in the wintertime. That means you want that sun to come into the space. So even if you have shading devices, it's not going to block that sun. So that's kind of a good strategy to work with almost all the time. You would see the psychometric chart. I also highlighted the space in this specific location. It is going to basically tell you for 4.6% of the occupants or 4.6% of the times, you don't need a specific strategy. It's already going to be comfortable inside the space. Evaporative cooling is not really going to help you in this specific scenario. Since this is a colder climate, internal heat gain definitely provides a lot of benefit, comfort to the space. Similarly, dehumidification would also add some benefits based on the climate studies. Similarly, you would see the wind analysis for each of the 12 months. Basically, what you're seeing here is the speed, the prevailing wind direction, and the speed or the velocity of the wind, basically, with the direction. That means if you're working on a master planning project, you're trying to understand, should we place the building in a specific direction? What months, maybe in the summertime, or maybe in the wintertime, you'll be getting a lot of wind from which direction. So you can provide fenestrations according to that and just respond to the behavior of the wind. And this provides you all that information. Perfect. I'm trying to see if there's any other questions here. I'm seeing a couple of questions on how do you really get access to the product? So what you can do is basically reach out to us directly. I'll either provide my email address or somebody from the sales side, their email address. They can definitely reach out to you, provide you more detail about how to get access to the tool. Just start experimenting. We'll provide you all the support that you need to get started with that, if that's helpful.
Also, Neelesh, there are 4 new questions on the chat.
Perfect, I see them. So one of the questions that I'm seeing is, do you know if the app integrating AI for so it's saying basically if you're integrating AI for the analysis, if so, is there a function that gives you the most efficient window to wall ratio options instead of having to test multiple options? So that's a great question. And I'm going to go back to the slide about optimization to elaborate on that piece. All right, so the app does use AI in some way. Basically what it's doing is, and if somebody has seen the Design Explorer, this is something similar to that. What's basically happening is you are trying to conduct a simulation, and that simulation is basically running thousands of options in the backend. So this graphic kind of shows all the different options, and I'll try to break it down for you so it's easier to understand. Let's say if you're looking at the first column here, we'll forget about everything else. We'll just look at the very first column. That basically says, if you're looking at the roof R value, we were able to optimize 4 different options for R values. Similarly, if you're looking at the glazing U value, there were 4 different U value options. Similarly, there's a wall R value. You can see there are 3 different options. What's happening here is that you don't have to manually add these options again and again. You will just add all the options you're trying to optimize in one go. What we do is basically create combinations of these options. So basically, in this case, there's like 1,000 options that have been created. You might select the option 1 from this guy, the option 2 from glazing, option 1 from wall R values. And towards the end, you would start seeing feedback, which is again really critical in terms of how many lead points does this achieve? What's the cost premium in terms of whatever the currency is? In this case, it's dollars. What is the payback in terms of years? So it's basically going to try and optimize and provide you some information about, you will have to provide some upfront cost in terms of the cost premium, which will lead to some energy savings in terms of cost as well. How long does it take for the energy savings to offset the cost premium that you're providing on day 1? And that's what the payback in terms of years would reveal. You would also see in terms of percentage of energy savings, and there are many options. There's a big range. You have some options that are giving you 0% energy savings. Some options are giving you 20% energy savings. You have already determined your target in the beginning for the building, because you know exactly what the 2030 baseline is. What is the 2030 target? Maybe so as to achieve that target, you're looking at a 15% or 20% savings. So you can pretty much go for those numbers. And towards the end, you'd see in terms of the EUI, we have a huge range. Again, based on some combination of these options, you will get a huge range of EUIs. In this case, it's anywhere from 40 kBTUs to 55, which is basically what the baseline was. And then you can actually select all these options and see if you had gone for the lowest cost bundle, you would have to make these selections of options for your buildings project. And that will lead to an EUI that's 51. And this is a cost premium. It's saving you $1 million. Or maybe you can go for the option 1 that basically says we'll bring the EUI down from 46 to 40. And in doing so, give you 22% energy savings. So you can basically pick and choose what options work for you and what doesn't. And that's just the power of the AI that we're using right now. So coming to the second question, the question is from the options you have shown in the last slides, does the recommended products and solutions, do the recommended products and solutions lower the EUI? That is adding a heat recovery unit for option D of the office pavilion. So that is a great question. I'm going to go back to the slide, just trying to locate that one here. Perfect. So I'm going to go one slide back. In this case, and this is a real project the project team is working on, one of our subscribers. What they did was once they provided a lot of solar PVs, they were actually able to offset most of the EUI in the project. That means they brought the EUI down from where they were, which was about 37, to about 7. So they got an EUI reduction of 30. The idea behind adding energy recovery was to just be able to reduce the EUI from wherever they were at that point in time to even lower. And just adding the heat recovery gave them a number that was below 0. So they were able to achieve a net positive building because now the EUI is a negative. It's a minus negative 1.52 kBTUs per square feet per year. Does that answer your question, Brian? Okay, so then I'll keep moving forward, but if you have more questions about this, I can definitely just circle back on this after I've gone through the remaining questions. The next question I'm seeing is there a metric that combines the heat gain from radiation, reflectance, etc., based on the window size and shading and the use of material types? So that's a good question. Let me just try and answer that question if I understood that correctly. So if you look at the total solar radiation studies for the project, that is basically going to tell you how much sun is falling on each of your facades. And the idea is to reduce the overall sun falling on your facades in the summertime. In the wintertime, you want some of the heat gain depending on the climate and location you're in. So you would be conducting all those studies, but then being able to conduct an actual energy analysis would reveal more information in terms of, for that climate, based on the heat gain you're getting, the amount of sun that's falling on the surface. This is what the internal loads, this is what the cooling load, heating load would look like. So if you're looking at the last graphic here, and I'm gonna go back 1-2 slides here. So this last graphic is basically telling you, is your building cooling dominated, or is it heating dominated, or lighting, or is it maybe plug loads dominated? And that basically tells you if you're getting a lot of heat. In this instance, it is saying this building is heating dominated. That means you have to provide a lot of additional heat, which also means you're actually losing a lot of heat, or there's a lot of exposed areas. If you have to provide a lot of cooling, that means there's a lot of heat gain happening, maybe from the internal gains, or maybe because you have larger windows, there's a lot of sun coming in. So there's not just one simple metric that can define that. You will have to see a combination of the different outputs to understand exactly what's going on with the building. I'm looking at another question here. It says, can this app be used for single family projects, or it is designed for bigger and complicated projects? So that's a great question. You can use this app for basically any type of project that you're working on. It could be office buildings, lab buildings, single family, mixed use projects, healthcare, education. There's, in addition to all the default options we provide, basically you can cover any building type you have in the AIA 2030, or let's say if you're talking about the CBEX 2003 data set, all the buildings typologies which have been reported through the CBEX would also be able to cover it. It's really easy to customize all the inputs when you're working with the app. And the last question I'm seeing, I think the comment is from Brian. They're curious if the tool recommended solutions as we test design. So that's a good question. Whenever you have to test certain options, you can just add those options. You don't have to re-import the geometry, nothing of that sort. Add a couple of different products to your project you can hit on the button recalculate, and that'll provide you the updated options. It's pretty much that simple. What's really critical about the optimization piece is that traditionally optimization is something that's not easy to conduct on every single project, because it definitely takes a lot of consultants, experts who can create these different models. So only bigger buildings with massive funding or cost were able to conduct these analyses and find the benefit in that. But because of the end-to-end nature of the automation that has been created, we can actually take it from a very basic geometry upload to the baseline energy model to the optimization piece all in one go. So you don't need to be an expert to conduct optimizations. You can still benefit from the power of all the optimizations you're creating, because now it's end-to-end automated for the users. Okay, I think that's all the questions I'm seeing. Is there any additional questions that you guys have? Okay, I saw one more question. Oh, that's a great question. So the question is, if, let's say, the users are interested in conducting the analysis, but you don't have the available staff to work on it, do we have consultants we can recommend? So we cannot really recommend consultants in the areas, although we have a lot of people on the app. At this point in time, we have about close to 20,000 users, active users, both engineers, architects, developers who are working through the app, trying to conduct these analyses on a daily basis and just making an impact. I would definitely say, let's say if you don't have the staff, when you actually start working with the app, it comes with a lot of support. So we would do workshops with you. You would have access to live support. So you can really send us a message during the working hours. We get back to you in 5 minutes or less. So we will never leave people hanging for 24 hours before somebody's there actively trying to help them with the issue. We don't expect users to be experts in energy modeling, experts in daylighting analysis, nothing of that sort. It has a very simple learning curve. You can just get on the app, start conducting these analyses. It takes about an hour or so for one iteration. That's pretty much how quick it is. And once the users have crossed the threshold of, let's say, one project, or maybe a couple of iterations, they're pretty much an expert. So they can pretty much take care of all the stuff themselves. In addition to doing all of this stuff, the app is designed in a way that as you go through all of these different analyses, it also educates you. So you're also learning more about these different metrics, how the reporting works, what metrics are more important for your project, or maybe for a specific climate. So there's a big educational piece at the same time. Perfect. So that's all the questions I'm seeing here. Is there anything that I missed? Yudiksha, do you have anything?
There were a few additional questions, but I answered them on the Q&A, so I think we're good.
Perfect, thank you. So what we will do is after the call, we will also send a follow-up email. So in case you're interested in pursuing this further or just trying to know more about this thing, we will definitely reach out to you. And we can always continue the conversation over there. I think Yudiksha put up my email and her email as well. So you can always reach out to us if you have any specific questions. I think the recording is going to be provided. It's being recorded, so you will get a recording link afterwards. But I think at this point, since we have 5 minutes left, I'm going to give it back to Rebecca if she has further comments or announcements she has to make. Right. Thanks, guys.
Thank you so much. Yes, the recording will be available. And just another huge thank you to Nilesh and Cove Tool for this extremely informative presentation. For those of you who are in attendance, AIA California staff will submit you for AIA CE credit, and it will appear on your transcript soon. As always, we just appreciate so much Cove Tool and the presentation that you provided. Like Nilesh said, that his email is in the chat there. So if you do have any further questions, go ahead and send him any of those that you do have. More information about upcoming webinars will be sent to you in a follow-up email, and we hope to see you on one of those future presentations. Thank you, everyone.